Welcome to Empowered Learning. This is the fourth video in the video series on Introduction to Hyperbolic Functions. So in this video, what we're going to do is focus more so on the inverse trigonometric functions. We're going to start off by evaluating a few using the logarithmic equivalent of the hyperbolic inverse functions. And then we're going to do some more derivatives and integrals with inverse hyperbolic functions, or in the case of integrals, we will take the integral of something to where its antiderivative will end up being an inverse hyperbolic function. So for our first example here, we see that we're dealing with tangent hyperbolic, well, the inverse of tangent hyperbolic, and we need to evaluate that at 1/2. So we need to reference to see, well, what is the logarithmic equivalent of this? So if we look here, we see that the logarithmic equivalent of tangent hyperbolic, or the inverse of tangent hyperbolic, is just going to be this particular formula here. And so I'm going to use the formula with the 1/2 on the outside just because it's going to me seem a little easier for me to do here. But if necessary, I'll go ahead and put the 1/2 back in there. So we see here that this just ends up being 1/2 natural log of 1 plus, in this case, 1/2 divided by 1 minus 1/2. Of course, here 1/2 plus 1 is going to give us 3/2, and in the denominator is going to give us 1/2. So that's just going to be 1/2 of natural log of 3. And so you could leave it that way, or if you want to, you could go ahead and rewrite this as natural log of 3 raised to the 1/2, which would just give you natural log of square root of 3. So whether you want to express the answer this way or express it this way is totally up to you. All right, so for our second example, we see that we're dealing with Cosh inverse. And so if we look here for Cosh inverse, we see that we have this formula here. Oh, and I forgot to mention this, even though it's not that important for the last example that we did. Notice that the value of y that we had here for our first example was 1/2. That actually fits within the domain of the function. And so I mentioned that to say that just because we have these logarithmic equivalents of what these inverse hyperbolic functions are, we do have to be mindful of what the domain of these functions are. Because we just, for instance, we can't take tan hyperbolic inverse of 2, okay? That's undefined. So we need to make sure that, again, we know the domains of the functions that we're dealing with here, okay? And of course, for the Cosh inverse function, we see that all this is fine, whether we want to express it logarithmically or as another hyperbolic inverse function like Cosh inverse here. Regardless of how we want to express it, in this example, we know that we have to be in between 0 and 1, where 0 is excluded, 1 is included. So whatever value that we have into Cosh inverse, we need to make sure that it fits within that domain. Okay. All right. So for example B here, we see that 3/5 does fit in between 0 and 1. So we will be able to do this. And so again, just as a reference here. So let's say we do Cosh inverse of x. That's just going to be natural log of 1 plus square root of 1 minus x squared, all that over x. And so if we apply that to what we see here, then this will be 1 plus square root of 1 minus 3/5. squared all over 3/5. And let's try to make that fraction in the denominator look just a little bit better. So now from here, we'll just, of course, do the arithmetic for all of this. And we know that 3/5 squared is just going to give us 9 over 25. And this will be 3 over 5 again. And that 1 that we have here, we could rewrite that as just 25 over 25. Make life a little bit more simple. So here we'll have natural log of 1 plus square root, and of course 25 minus 9 is 16. So this will be 16 over 25 here. And that's kind of getting out of hand, so I'm going to try to rewrite that and make it look better. So we got 1 plus square root of 16 over 25. Yep, looks a lot better. All over 3 over 5. And of course, square root of 16 over 25 will be the same as 4 over 5. And that 1 there again, we could now take that and rewrite that as 5 over 5. And so now this makes this natural log of 9 over 5 divided by 3 over 5. And if we take 9 over 5 and multiply it times the reciprocal of 3 over 5, which is 5/3, we'll just end up with 9 over 3, which is just 3 inside of the logarithm. And that will be our final answer for that example. Okay, so for our next example here, we're being asked to take the derivative of Cosh inverse of secant x. So again, this is one of these examples where we have a hyperbolic function and a trig function kind of mixed together here. So we need to make sure that we remember what derivatives go with what. So just like how I did in an earlier video on examples like this, the first thing we're going to note is that if I take the derivative of Cosh inverse here, then that's going to be 1 over square root of x squared minus 1, okay, like that. Also, we know that the derivative of secant is just going to be secant tangent. Okay, so with that being said here, we have what we need. We know that we're dealing with a composition function here. So we know that we're going to have to use a chain rule. And so we got dy over dx. We're going to take the derivative of Cosh inverse with respect to blah. And so that'll be 1 over square root of blah, which is secant squared minus 1. And then we're going to multiply that times the derivative of what secant is, which is just secant x times tangent x. Okay. So now at this point, we look at the denominator here and we're like, yeah, that's probably an identity. And so since this is regular trigonometry here, we'll start off with sine x plus cosine x is equal to 1. And what we would like to do is have something that has secant squared in it. So that's going to be the reciprocal of cosine. So we'll just divide both sides of this equation here by cosine squared, and I'm just using c for that. So this will end up being tangent squared plus 1, which is going to be secant squared, okay? And of course that t squared there just represents tangent squared, so I'll go ahead and write that in. Okay, and so now we know that if we rearrange this equation here, that tangent squared of x is just going to be secant squared minus 1. So we're saying all that to say here that under the radical, we're going to replace all of that with just tangent squared of x. So we'll go ahead and block this off here. Do an equal sign and then come down here. And this will be secant x times tangent x, all that over square root of tangent squared x. And so here, we'll rewrite the numerator. And we know that the denominator here for square root of tangent squared is just going to be absolute value of tangent. So now at this point, we're tempted to just drop the absolute value signs off of this tangent x in the denominator, but we need to be careful about that to make sure that if we drop it, we know for what x values that's actually going to be valid for. So in looking at this, what we really need to look at here is what our function looks like, after we've, taken the derivative of it. Okay. So if we look at the derivative, we see that we end up having the square root of secant squared minus 1 in the denominator. And so what this roughly means for us is that we know that this derivative is going to be defined as long as secant squared of x is going to be greater than 1. And of course, if we look at a graph of secant squared, and I'll just sketch one really quick. So graph of secant will kind of look like this, where the y values for all these points that I have down here are 1, and these are vertical asymptotes. This one that I'm drawing here is at pi over 2. This is at negative pi over 2. This is at 3 pi over 2, negative 3 pi over 2. So the point that I'm trying to make here is that the only time secant squared is going to be not greater than 1 is when secant squared is exactly 1, and that are at these points here. Okay, and those points, the corresponding x values for that will be 0 here. This will be pi here. This will be minus pi here. So we have integer multiples of pi is where that particular function is going to be undefined. So other than that, I know that this function is going to be, defined, and thus here I can remove these this absolute value sign from tangent as long as we know, hey, any value of x that we plug in that is integer multiple of pi, the function is not going to be defined at all. Okay, so we're going to remove these absolute value signs with that understanding. Okay, so that'll be secant x times tangent x here, and of course this will go to 1. And we'll say that the answer of this is just going to be secant x, where x is going to be able to be any real number. So we will express it this way. So here, as long as the x values that we have are not integer multiples of pi, we know that this result here is just going to be secant x. So we know that we're good to go there as long as that happens. All right, so for our next example, we're just going to take the derivative of this two-term function here. So for the first derivative here, we know that we could rewrite square root of 1 plus x squared as just 1 plus x squared raised to the 1/2. We'll be taking the derivative of that. We also know that the derivative of the inverse of sine hyperbolic is just going to be just 1 over square root of 1 plus x squared here. So we know that's going to be the derivative of that. Since we're dealing with a composition function here, we'll have to take the derivative of the inside function too. So we're going to look at this way first. So I'm going to rewrite it like this first. And then we'll go ahead and take the derivative. So for this first term, we'll have 1/2 times 1 plus x squared raised to the negative 1/2 times derivative of the inside function. The derivative of 1 plus x squared is just going to be 2x. So that'll be our first term. For the second term, we'll take the derivative of the inverse of sine hyperbolic, where and we know that that's just going to be 1 over square root of 1 plus, and of course the x here is just going to be x raised to the negative 1. We'll take that and have that squared. And then of course from here we'll go ahead and take the derivative of the inside function, and that's going to be a minus x raised to the minus 2 when we do that. And so now it's just a matter of us cleaning all this up and making it look nice so that we can simplify it into something that will be useful and not so cumbersome. So we see here that we have some reducing that we can do here. And so for this first term, we'll end up with just 1 over, this will be square root of 1 plus x squared here. And then, of course, we have another x that's laying here, so I need to go ahead and add that. All right, and so for our second term, we see we have a negative times a negative, which will end up giving us a positive here. And we have x raised to the negative 2. And this will be over. And this will be square root of 1 plus x raised to the negative 2 here. All right, so at this point, we just need to rewrite this. So we'll keep the first term the same for now. But the second term, one thing that we can do with it is realize that x raised to the negative 2 is just the same as 1 over x squared. Okay. And then because we have that, we can rewrite this 1 here as x squared over x squared. And then from here, we'll start to see that some simplification can start to happen. I'm going to go ahead and move this x raised to the negative 2 down to the bottom here. And I also note that I am going to have this times square root of x squared plus 1 over square root of x squared. Okay. And so with that, we continue on. First term will stay the same. For our second term, notice that we'll have a 1 over x squared times square root of x squared plus 1 over absolute value of x. And let's make that look a little better here. So now we just need to go ahead and finalize this, make like terms, we'll find a common denominator in the denominator, and then finish up here. So let's bring this down. And so one of the things that we can note here is that this not square root, but absolute value of x can be moved up to the numerator here, since all this is being multiplied in the denominator. So I'm going to go ahead and do that now. Don't know what happened there, but okay. So here I'm going to erase this, erase that, and I'm going to put absolute value of x here like this. And so now from there you see that we could have like denominators if I was to multiply the numerator and the denominator of this first term here by x squared. So if we do that, then final answer ends up being x cubed plus absolute value of x, all that over x squared times square root of 1 plus x squared. Okay. And so the reason I'm going this route instead of at the point where I had that absolute value and I would just try to simplify it and drop the absolute value signs there is because what we have to realize is that both here and here, as long as your values are not 0, you can pretty much plug in anything that you want. Okay. So, and if you look at the domain for the derivative of hyperbolic sine inverse here, you'll see that again, because that x is squared, you can plug in any x value that you want that is positive or negative. You will never get 0 in the denominator, so you can plug it in and it will be, anything. Okay. Now the thing is that's not controlling whether this function is going to be, negative or positive in some instances. And thus, whenever we add, this up, we don't know if this term here is actually going to be positive or negative. So, of course, we have the absolute value sign. So we would like it to be, non-negative all the time. But the point that I'm trying to make is if x is negative, then it means that this x cubed here is going to be negative, even though this second term in the numerator is going to be positive. However, if x is positive, then it means both the first and the second term is going to be positive. And so we have to account for that. Okay. And so that's why I'm not just simplifying and saying, hey, let's drop the absolute value signs. And when we had this down here, like this, just get rid of the absolute value signs and just say, yep, all this is just x. So that's why I didn't do that, because if we do that, we're assuming that x is always going to be a non-negative number. And according to what our function and the derivative says, that's not necessarily the case. Okay. So this is the correct and complete final answer for this derivative. All right, so next we're going to switch gears here and evaluate some integrals where the antiderivative that we will need to take is going to involve being some kind of hyperbolic, some inverse hyperbolic function. So we see here to start off that this denominator here looks like something familiar that we could work with. So here we know that if we were to be able to write this as square root of 1 plus something squared, then we know that that would work out well for us, because we know that the derivative of hyperbolic inverse of sine is just going to be 1 over square root of 1 plus x squared. Okay, so therefore this means that the antiderivative of 1 over square root of 1 plus x squared is just going to be sine hyperbolic of x. So we're going to try to work it out to where it will meet that profile. So here we know that 4x squared is the same as 2x quantity squared. Okay, and so from there we see that if we were to allow 2x to be substituted for some simple variable like u, then we can get this into the form that we need to get it in. So here we're just going to do that. So we'll say let u equal 2x, which means that du is going to be 2 dx, or 2 times dx. And so from there we could replace dx with just dx with just 1/2 du. So let's go ahead and divide both sides by 2 there. So we'll do that. Of course, all of this will just be 1/2 du. This in here will just be u. And of course, we could also go ahead and figure out what our new limits of integration would be in terms of u. So we'll say also u of 0 still going to be 0. And we'll say u of 4/3. That'll be 2 times 4/3. And that'll be 8/3. So therefore, our new integral here is just going to be, we'll go from 0 to 8/3 now. And we'll have a 1/2 du over square root of 1 plus u squared. And then from there, we know that this would just be 1/2 of, and the antiderivative of 1 over square root of 1 plus u squared will just be inverse sine hyperbolic of u, and that'll get evaluated from 0 to 8/3. And so then all we do is substitute in. So do 8/3 first, minus sine inverse of 0. And we'll see here that whenever we plug in, well, I'll put it like this. So we know since sine hyperbolic of 0 is 0, then that means the inverse of sine hyperbolic of 0 will still be 0. Okay, so we'll automatically know that. So we're going to save some time and space by using that. Now, of course, for sinh inverse of 8 divided by 3, remember, we do have an equivalent way that we could write all of this in terms of logarithms. And so we'll go back and look at what that particular formula is, and then we'll move forward. All right, so you see here that for sinh inverse, we have just natural log of the sum of y and square root of y squared plus 1. And of course, instead of y's, we're going to have u's this time. So that is what we're going to use here. So from here, we'll go ahead and rewrite all that, and I'm going to switch colors. We'll say this is just 1/2 of natural log of 8 divided by 3 plus square root of 8 divided by 3 squared plus 1. All right, and we'll close that off there. And so now this is all that we need to evaluate. And so here we'll have the 8/3 again here. And of course, square root of, 8 over 3 squared is going to be 64 over 9. And this 1 here can be rewritten as 9 over 9. And so here this could be 1/2 of natural log of 8 over 3 plus, and 64 plus 9 is 73, so this will be square root of 73 in the numerator. In the denominator, of course, the denominators are the same, so we'll just have square root of 9, and square root of 9 is just 3. And so then, since the denominators are the same, and we have this 1/2 out here, we could really rewrite this as natural log of square root of 8 plus square root of 73, all that divided by 3. And that will be our final answer in a nice compact form. So for our last example in this video, we see here that we're asked to evaluate the definite integral from 0 to 0.5 of 1 divided by 1 plus x squared dx. And so here we note that, of course, the derivative of inverse hyperbolic tangent is going to be just 1 over 1 minus x squared. So we know that the antiderivative of 1 over 1 minus x squared is just the inverse of tangent hyperbolic plus some constant. Since we are using, or since we have a definite integral here, we won't have to worry about this integration constant. And therefore, we'll just take the antiderivative and evaluate it from 0 to 1/2. And of course, here we know that since tangent hyperbolic of 0 is 0, the inverse of tangent hyperbolic evaluated at 0 will still be 0. Okay, and all we're left with is just the inverse of tangent hyperbolic of 1/2. And of course, we have an equivalent way to write that in terms of logarithms. And so here, if we switch over, we'll see that, yes, the way that we can rewrite the inverse of tangent hyperbolic will be like what we're seeing here. Basically, the natural log of square root of the quotient of 1 plus y and 1 minus y. So we could just do that. And everywhere where we see the x, we can just put a 1/2. So we see that that's what this ends up looking like. And once we work everything out here, we see that we still get that natural log of square root of 3. And so with that, this concludes the part 4 video on examples of derivatives and integrals, as well as evaluating inverse hyperbolic functions. And so hope this helped. I have one more video that I'm going to do that's going to be a part of the series. That's going to be more so for showing you how we actually come up with some of the differentiation rules for some of the inverse hyperbolic functions. And so, of course, for most of you, you probably won't need to know that, but I'm doing it just in case you may have to do an assignment like that. All right, take care.